Hello, welcome. Today we're going to look at something called the work kinetic energy theorem. So this isn't really anything like new. This is stuff that could work out through other ways. So just depending upon what type of information you have in a given situation, this work kinetic energy theorem can make a process a lot easier than what would be doing through some of our previous methods. So like the work kinetic energy theorem, as you may guess, involves work and kinetic energy. So what it's saying is if you're looking at the network done on an object or in a system, that's going to be equal to that change in kinetic energy. One main thing, there's a limitation on this, is we are talking about the network. So it would have to be the work done by the net force. So if you're dealing with the net force, which we've frequently seen in different circumstances, like if you have friction slowing an object down, when you look at your free body diagram, that's typically the net force. So then this would be the net work done by that. But if you do have multiple forces going on, like a force of an engine, and the force of friction and something's accelerating, those two would not be equal. This work kinetic energy theorem would not be applicable, but in most cases it would be. So depending on what you know, this can be a lot easier way to work out and figure out what work is. So let's say an example here, we want to figure out what is the work done by a cannonball, or I should say on a cannonball, really, I should say what is the work done on a cannonball that launches a 6.5 kilogram. Oh, by a cannon. Yeah, that makes sense. All right. What is the work done by a cannon that launches a 6.5 kilogram cannonball from a rest to a velocity of 85 meters per second in 0.45 seconds? So I'll give you a moment to sort of jot that down, or at least get the relevant information. You can pause me, of course, at any time if you want. Based on what we've been doing so far in class, if we're looking at work is force times distance, or Fox. So in this case, we don't know the distance, but it's a one-dimensional motion thing. We got a 85 meters per second is our final velocity. We got a time. We know it started at a rest, so our initial velocity. We could figure out distance, and then in order to figure out force, force is Newton's second law. It says mass times acceleration. So we could use that. It's more one-dimensional motion stuff. Go through, solve for the acceleration, do our mass times that acceleration times that distance we found. We got work. It wouldn't be too bad, but we'd have to find a couple things along the way. The easier way, though, in this circumstance, is we can look at this work kinetic energy theorem. And if we know our change in kinetic energy, we could figure out the work. And that would be a lot easier with this given information. So in that case, we could figure out that the change in kinetic energy would be our final kinetic energy, 0.5 or 1/2 mass times the final velocity squared, minus our starting kinetic energy, 0.5 times mass times the initial velocity squared. And we know everything we need for those. We know the mass. We know our final velocity is 85 meters per second. We know our mass again, and we know our initial velocity is 0. So we could plug those numbers in. If we do 0 for our initial velocity, that initial kinetic energy, the whole thing will just be 0. So we'd just be doing 1/2 6.5 times 85 squared. Typing that in, doing our sig figs in units. Should be 2 sig figs looking at all the numbers given. And our units for work is joules. So if we look at that, 23,000 joules. And that's a lot easier, a lot faster than it would have been to find that distance, to find the acceleration, to plug all that in and work it out. But if you wanted to, just for fun, you could work that all out and should get the exact same answer. You might notice when we did ours, we were given that 0.45 seconds. We never used it. But if you did go through figuring out the distance using that, figure out the acceleration, you would end up getting the exact same 23,000 joules. Sort of cool that it would work either way. So that's our work kinetic energy theorem. Remember, it works for network, which will frequently be the case if you're talking about forces and work done. That whatever force is involved would be our net force. If it weren't for some reason, then you wouldn't be able to use this. But in a lot of cases, with given information, this will probably be a lot quicker and easier than some other methods. But you can still do things lots of different ways, which I think is always sort of cool to realize. There's not just one way to go through and do something. So good luck with that. Talk to you later.